Let's talk now about titrations. Titrations are extremely useful analytical techniques that allow us to calculate the concentration of an unknown solution, whatever it may be, of whatever analyte we're looking for. And so very experimentally useful, very useful for talking about pH, but you can also do them with redox reactions. But for right now, since we are talking about acid-base equilibrium, or like more stuff about acid-base equilibrium, we'll do that in the context of acid-base. So we can do titrations in a couple of different ways. And we'll look at each of several cases. Typically, we are going to be, we'll have a known volume of acid to which we are adding base and evaluating how the pH is changing. That's standard. You could, of course, do the other way around. You could have a known amount of base to which you're adding acid and watching the pH change over the course of adding that acid. That works too. But like the rest of this, we always focus on the acid, so we'll have it that way, where we'll be titrating various acids with strong bases. So let's talk about the first one. So strong acid and a strong base titration. So if we take 50 ml of 0.1 molar HCl, that's a strong acid, and we add 0.1 molar NaOH, we can evaluate what the pH would be at any point along this titration. So when we add 0 mLs of base, when we add 25 mLs, when we add 32.74 mLs, when we add 50 mLs, when we add 62 mLs, whatever points we're interested in, we can evaluate the pH. And we'll see that strong acid, strong base titrations generally follow the same pattern. We'll see that if we were to graph the base added with the pH of the solution, assuming we're starting with 50 mLs of 0.1 molar HCl, our pH should be 1, right? So if we're going from 0 to 14, not 4, 14, we'll be starting somewhere around here, right, at around 1, where we have added 0 mils of NaOH. And for right now, we'll just include 50 because that'll be our point at where we've neutralized the solution. Because 50 mils of 0.1 molar HCl will react with 50 mils of 0.1 molar NaOH. These usually don't have limiting reactants or anything like that. The theoretical yield is very, very high, as is the actual yield. So with these, they work out really well. So we're going to see that as we add NaOH, we don't really see much change happening. We see some gradual change maybe as we're adding NaOH. And as we get very close to 50, our graph suddenly will shoot up and will then mirror itself on the other side till we add maybe like 100 or something, at which our pH would be 13. Well, a little bit less because of all the extra volume. But the point is, notice some patterns here. We're going to be looking at a few key points along our titration. The first one that we probably will notice is that presumably, if I've drawn this correctly, we'll say that I did. Here we are, right here, because 7 clearly is right up here. Yeah, we'll just kind of fake it. There we go. Notice that once we have reached what's called the equivalence point, that's the equivalence point there, we have added exactly the same amount of base as acid, moles. So we've added the same amount, because they were the same molarity, we've added the same volume. And so therefore the moles are the same as well. That means the moles of acid and base are the same. Let me just write that down here. And at the equivalence point for a strong acid, strong base titration, we would expect it to be a pH of 7, right? As HCl and NaOH react, we make NaCl plus water, We know HCl is a strong acid, NaOH is a strong base, NaCl is negligible. It is neither acid nor base. It is going to end up giving us a neutral solution. And because of that, because we have negligible acid and base as our conjugates, our pH at the equivalence point should be just about 7. And the important point here is that we see that there's this very sharp curve. Right? As we approach that equivalence point, at that point we get this sudden skyrocket in pH. Because pH is a logarithmic scale. So that means that these small concentration changes eventually make a big difference, right? So at this point, we have mostly HCl still around. We have some NaCl. And as we go past the equivalence point, at the equivalence point, we only have NaCl. We have no HCl and no NaOH, just sodium chloride, because they will have completely reacted together. And as we pass the equivalence point, we have mostly NaCl plus some NaOH. So we start getting more and more basic, so we start seeing our pH at the very high end. And so eventually we'll end up petering out, but we'll see that over time, we're changing the composition of our solution. So from one that's mostly acid to one that has neither acid nor base to one that's mostly base, right, as we keep on going throughout this. So the patterns here. When we look at the initial pH, it's very low. That's one thing to look at. We'll look at a lot of characteristics throughout these titrations. So initial pH is low. Because we have a strong acid, we're expecting it to be very acidic. We'll see that as we approach, that kind of spelled correctly, as we approach the equivalence point, the pH drastically changes. It drastically rises. At the equivalence point, pH is 7, because we're only seeing NaCl in there, negligible acid or base. And then finally, above equivalence point, pH drastically rises again, very dramatically until we kind of reach our kind of end point, as it were. So wherever we decide to end, we're going to rise drastically just in the last couple of mLs right after the equivalence point, and then we kind of level off again. So these are kind of things we're looking for. We see that the initial pH is low. As we approach the equivalence point, the pH drastically rises. The equivalence point itself has a pH of 7. And then just above the equivalence point, our pH drastically rises again until it levels off. So that's what a strong acid, strong base titration looks like. In our next video, we'll look at some calculations associated with this, just so we can establish where this graph came from.